So last time was just kind of going over the basic theory behind diffusion weighted imaging. So how do we prepare the spins so that they have a weighting dependent on the tendency to diffuse in a particular direction. And so what I want to talk about today, three different things. So first thing, so last time we talked about some rotationally invariant measures, the mean diffusivity and fractional anisotropy, which are two measures that you can extract after you've found this diffusion, Gaussian diffusion ellipsoid. But those measures, both of those measures, just kind of toss the information about what the diffusion direction is. And so you can use that information to try to follow tracks around. But before we talk about that, I want to talk about like how do you actually trace tracks neurobiologically, and what's the relationship between track tracing with diffusion imaging and what I call real track tracing. So that's the first thing. And then the second thing, I'll talk about length scale, because you can do different small b's and possibly discover something about several different mechanisms of diffusion within a single voxel. That's what that's about. And then finally we'll talk about some practical, what are the actual pulse sequences that we actually run to measure diffusion? What do those actually look like? So starting off, we'll talk about real track tracing. So how do you do what I call real track tracing? So say you've got there's an area, little area MT in primates. All primates have that, and that's an area. It's involved in detecting motion, and so how would you actually figure out what the connections of that area are? You would get a micropipette, a little tiny micropipette, goes down to just a couple microns at the tip, and you would inject some kind of dye into there. You could also inject something like horseradish peroxidase and then visualize that. A number of different things you can do, but how does the dye work? So you say you injected it into area, MT. So the way these dyes work is that, say we're in the cortex. So you've got like a pyramidal neuron over here, and there's it's got all these dendrites, little spines on them, and then the axon comes off, and then it goes someplace. And then there's, maybe a long distance away, centimeters away, it will come up into the cortex and then make some synapses. The axon, the myelination will go away, and then you'll get like, a couple thousand synapses. The little balls are the synaptic bouton. So it turns out if you inject so this guy, is the axon terminal. Axon terminal. And here's, cell body. So if you inject one of these dyes into the cortex, they take advantage of the fact that if you look at the axon, there's actually transport both directions, bidirectional transport in the axons. And so why is that? Well, the DNA, which is making the mRNA, which makes proteins, is generated in the nucleus, and the the mRNA and the proteins have to be transported down to sort of to the business end at where the axon terminals are. But then you've also got stuff transported backwards, like waste products and other things. So there's actually two-way transport. So if you inject a dye anywhere, typically what happens is, if you inject it where there's cells, you're going to see some dye going down the axon this way. If you inject it where there's axons, you'll see some of the tracer ending up in the cell body. So I call this, real tract tracing, because you're actually in the tract, meaning you're actually in the actual axon. This is the axon here, and so if some dye appears, you know that an axon had to have been here because the dye went through it. And there's a number of different very cool, slightly dystopian methods of doing more advanced tract tracing that involve viruses. So if you look at something like rabies virus, so rabies virus it's a neurotropic virus. It likes to sort of get into neurons. And so what you can do with rabies virus, you can inject some rabies virus over here, and then what will happen is rabies virus will get into, it likes neurons, it gets into the neurons, it gets down to the cell body, and then when it gets to the cell body, it's a self-reproducing tracer. So once it gets to the cell body, it makes more rabies virus, and then what can happen is that rabies virus can come out of the synapses. So there'll be some synapses from another cell, some other cell that's synapsing on this, this dendrite right there. And the rabies virus can actually go backwards through the synapse into that other cell, and then, go back to that cell body and then reproduce there. So it's transsynaptic. And that's kind of like why it's not good to get rabies, because if you get rabies, it comes in through one of your neurons. You get bit by a dog, it comes in through one of your neurons, eventually it gets into the spinal cord, then it goes up the spinal cord, gets into the brain. Before you know it, there's like rabies all over the place. Not very good. But it takes about a day, about a day per synapse. So this is a very powerful technique, because you can actually see what's really hooked up to what. Because if you inject some of it here, one day later you'll find the cells that projected to that point. 2 days later you'll find the cells that projected to the cell that projected to that point. 3 days later you'll find the cells that projected to the cells that projected to the cells that projected to that point. I mean, it's an incredibly powerful technique. That's what we call sort of real tract tracing, because you really are tracing the tracks. What we do with MRI it's a slightly higher level, sort of more generic kind of. It's not really tract tracing. It's kind of like sort of tract generalities. And so how does that work? So that works by essentially taking that diffusion tensor, or as we'll see, something even more complicated than a tensor, and then trying to actually just trace through the brain. So if we just draw it out in just 2D. So here's a bunch of voxels. So at each voxel, what we can do is calculate our diffusion tensor, our little diffusion tensor pill, ellipsoid. And that ellipsoid, I'll just draw it in 2D, but it's actually in 3D. And the idea is you've got, at each place, you've got a little ellipsoid, especially if we're in the white matter, that's elongated. And here's the ellipsoid here. There's one there. Here are just a bunch of ellipsoids. Those are supposed to be ellipsoids. That guy looks like a kidney bean. Okay. So you'll have this except, in 3D. You'll have some field of little, one ellipsoid in each one. And then what you can do is you can put a seed someplace. So, let's start off by, putting a seed here. And then what we do is we just try to see, where is the next, where is the next likely place that the axons within that voxel went? And you would say, like, well, they probably went there. And then now, they could have gone there or here. Let's say we estimate that they went here. And then we estimate that they went over here. And so the idea is you just go through your whole data set, put seeds all over the place, and then just trace your tracks through there. So there's a number of sort of problems with this, which we can sort of put up here, problems. So the first problem is that there's different ways of doing tract tracing, but the most basic way I described here you could call a Markov process. And what that means is some kind of process that doesn't have any history to it. So in other words, like, you've got a seed here, and then you choose where your next point in your tract is, and then at that point there's no history. Now we just go, let's just choose where the next point after that is. So a process like that basically has no history, that just depends on just the previous, it has history, but just only like one, the idea is it has like a one-time point history. The problem with that is if you get off somehow, then you could potentially, so let's make this guy just a little bit more ambiguous, so we don't know exactly which one this is supposed to go to. So say that one was a little bit like that. So the problem with a process like this is, this guy is, if we went this way, we're heading off, somewhere else, completely different than this tract. And so we could get far off just by having made one mistake. Now, there's various ways to try to fix this. You could take both paths, for instance, and just sort of have a probability of where the paths go to. There's all different kinds of ways of fixing this, but one of the fundamental problems is that when you have something like this, where like one error at one point, can be made, you can sort of propagate that error in a complicated way, and end up like in a completely different place than if you had taken, the rightward pathway. So that's one problem. But another problem is crossing fibers. And so one of the things that I mentioned last time is that when we model diffusion as Gaussian diffusion, what we're saying is that the diffusion is basically, it has a Gaussian profile. So, what that means is you'll have this little sort of pill-like surface of the three eigenvectors, defined by the three eigenvectors. And what are those defining? This is the first eigenvector that defines a Gaussian profile of the probability of a particle ending up at a certain distance. That's what the meaning of that is. And then the other axis, so say here's the second eigenvector, which is perpendicular to the first one. That one will have a Gaussian, a smaller Gaussian that, and then there'll be a third one, for our third eigenvector that say sticks out. Those are all perpendicular to each other. That would be the thinnest axis of the pill. But that is not necessarily a good model for the diffusion within a voxel. So it could easily be the case that you've got axons sort of going at right angles to each other through a voxel. And in fact, not only is that possible, but that's actually probably the default situation. So if you look in the brain, if you actually take sections of the brain and look at it, you often find, say you look in the brainstem, you'll find like a whole bunch of fibers sort of heading, vertically down the brainstem, and then there'll be sort of a horizontal mesh of axons almost perpendicular to that. You can see the same thing in the white matter. It's very common for there to be sort of interpenetrating axons that sort of go through each other at roughly right angles. And why is that? Well, one reason is that if you're an axon, so here's an axon, you got a little growth cone, and you're sort of growing someplace, and there's a big bundle like this. Well, you can, if you look at actual axons, they often run in bundles like that. Now, say this guy is actually supposed to go to some structure over here. He could sort of accidentally get caught up with this bundle and then crawl along the bundle and get lost. And so there's probably some actual benefit to just going like, I'm going to really break with the crowd and just go through them at right angles and don't pay any attention to all those guys going the other direction. And so you see this a lot. Actually, if you just look through the microscope at axon bundles, you'll see that there'll be an axon bundle like this, and then sometimes an axon will turn out of it at a sharp angle, or other axons will just sort of go right through it at right angles. So that's actually pretty common. So this kind of Gaussian, this is called Gaussian diffusion model. It can have different Gaussian sizes in different directions, but fundamentally it has to look like a Gaussian. So it's possible to just collect more diffusion directions, and then you could make a non-Gaussian model. So if you make a non-Gaussian model, what does that look like? Well, you have the same setup here, but if I just sort of do it in, let's just do it in, rather than making an ellipsoid, let's just do it in 2D. So if you measure diffusion in more directions, there's no reason you can't measure diffusion in more directions. So say, for instance, there was some diffusion in that direction, and then there was more diffusion in this direction, something like that. And that's going to be symmetrical, so it's going to be something like this. So how would you, now, if you tried to characterize, yeah, everything good, David? Oh, stay still for focus, yes. So if you try to characterize this this situation with a Gaussian pill, it's obviously going to make the wrong choice. It'll just say, well, this is the best pill I could fit to that. So this would be, a Gaussian approximation to that actual distribution of diffusion directions. And that's not the right one. Now, how would you actually measure this more complicated thing? You'd have to measure diffusion in a bunch of different directions. So remember, you only have to measure a hemisphere. So you'd measure that direction and this direction. These are all the measurement directions in that U vector from last lecture. So if we measure diffusion in all those different directions, we could end up with this diffusion surface. And the diffusion surface would then actually characterize what's there. You'd have to measure like 64 directions or 128 directions, and then you could actually pick up. So if you measured 64 directions, you could pick up two directions, two principal directions that were present in this voxel. And if you did that, then you could sort of deal with this problem of crossing fibers, because it may be the case that, in fact, the real distribution here, had a little bump on it like that. It wasn't an ellipsoid. And maybe this guy had a little bump on it also. And so what that would imply is that actually there's another fiber tract coming through here that's actually going, to that guy. And so that's another problem. So when you look at the programs for doing tract tracing, sometimes they allow you to use a non-Gaussian model. Sometimes they just use the extra directions to do a better estimate of the three principal axes of the ellipsoid. And that's the common thing to do, because if you just measure 6 directions, you can get the 3 principal directions of the ellipsoid. But if you measure 20 or 30 directions, you'll get a better estimate of what the direction of the ellipsoid is. Obviously, you got to deal with a lot more pain here, because now there can be tracks, multiple tracks going through a single voxel. That's actually, for sure, what's actually going on in the real brain. But you can sort of see some of the issues. There's another issue that you could call the freeway ramp problem. So one of the problems is axons often run in a bundle, and then they just peel off at some point. I mentioned that before. So what will happen is, some axons will come from a structure here, and they'll go join a bundle and go for a while, and then maybe go off to some other structure here. And then you'll have another different structure, and that'll send off axons. They'll join this bundle, and then maybe they'll turn off over here. And the problem is, if you've got a voxel right here, within that voxel you can't tell who's who. So if you see this kind of structure, you have to sort of essentially allow that voxel to have axons that go to both places. And that's actually another very common thing. You see these bundles that contain multiple different substructures, 20 or 30 different sub-bundles that are going to different places. And if you want to hear about those, look at my systems neuroscience class about say the medial forebrain bundle. It's got about 20 or 40 different components in it that are going different places. So that's another problem. And then finally, there's another problem is sharp turns into gyri. So what this problem is if you look at a typical gyrus here or something like that, and then look at how the axons come up into it. What they look like is they'll all be coming up, and they'll run sort of parallel to the so this is the gray matter and the white matter, and they'll run sort of parallel to the sort of axis of the gyrus, and then they'll suddenly whoop, just turn off like that. And another one will come up like this, run right along underneath the white matter, and then just go something like that, or maybe they'll just go like that. And so one of the problems, those sharp turns, one of the problems is that those are very difficult to pick up with a tract tracing, sort of a voxel-based tract tracing method like that. And so there's a lot of ambiguity about, if here's a voxel and you're tracing some axon tract in here, there's a lot of ambiguity about which side of the gyrus does it go to? Does it go to this side of the gyrus, or maybe it went to the top of the gyrus, or this side of the gyrus? So there's a lot of ambiguity there. But as I say every year, I've made my peace. I started off as more of a neurobiologist doing this kind of thing. I've made my peace with DTI, MRI-based tract tracing. It's finding something. It's really not finding the exact connections, but it's finding something at a slightly higher level, but it's a pattern of connections. So if you look at it, one brain, you can say that this brain has a very strong tract here, and you look at this brain, and that same place in the brain, the anisotropy isn't as strong, or the number of bundles that we trace through there with the tract tracing program isn't as great. There's differences. Now, are they exactly indicating connectional patterns between different parts of the brain? No, they're sort of at a slightly more generic level, subject to all these various problems. But as long as you sort of realize that these are the problems, then I don't have any problem with tract tracing. But that's sort of a contrast between like, the actual tracks of axons, which you can really just discover with injecting a dye, versus this other slightly higher level method of trying to figure out where the tracks are. So, okay, any questions about tract tracing? So that's using the eigenvectors. So this is use eigenvectors or diffusion surface, which is even more. So use tensors or use something that's even more than a tensor, because this is actually sort of like a super tensor because it's got a whole surface of possible diffusion directions. So any tract tracing questions? So there's a lot of software to do this once you've collected a bunch of diffusion data. Okay, so the next thing, quickly talk about, is length scale. So this is one way of trying to kind of subdivide non-Gaussian diffusion, is one way of trying to subdivide the more complex diffusion situation within a voxel. But another one is by using multiple b values. So what are we trying to do there? The idea is that, as I mentioned last time, there was a voxel that's got a bunch of crap in it, and so it's got cells in it and axons going through and other axons going through, and a bunch of axon terminals and local circuit neurons that are doing something. So, and then all of that is embedded in fluid, and so you've got sort of fluid around the cell, and that the atoms and molecules there are able to diffuse more rapidly than the atoms and molecules inside the cell, because the ones inside the cell, there's a bunch of biomolecules that they're bumping into, and so the diffusion doesn't occur as rapidly inside cells. And so the question is there any way of trying to fish those things apart? And so our basic equation was, the attenuation, atten, as a function of the diffusion coefficient, was equal to e to the minus b times the apparent diffusion coefficient. And what sort of like the gross kind of things that we're trying to distinguish, a high, apparent diffusion coefficient means fast diffusion. You could call that extracellular. Fast, extracellular. A low apparent diffusion coefficient, small, is means slower diffusion, and we could sort of call that intracellular. We're not really distinguishing those actually, but grossly. And so what is that equation? That equation is just an exponential fall off with both b and d. So you got two numbers there. And so if we just look at our first, if we just plot that out, so we're used to plotting out e to the minus t, right? And so we usually have t over here. But now what we've got here is, b and d. Right? Both of them sort of behave the same way. And what kind of graph do you get out of that? Well, you get just the regular sort of exponential decay. That's what that equation is. And what is, so here's our signal. And so the idea is that as the diffusion increases, as as the diffusion coefficient increases, the signal falls off. Instead of falling off with time, it's falling off with increased diffusion. So what did, so I always make a joke, like, what do physicists do? They don't usually record the whole brain. Why? There's a whole bunch of different parts of the brain. Why don't we just record one slice a lot? And so they get one of their physicist friends to stay in the magnet for about 2 hours. And then let's hammer away at that one slice so we get some really good data. And so why not just record a whole bunch of different B's. So that's the strength of the gradient plus the timing of the, how long the gradient was on plus what the time between the two gradient lobes is, all put together into a single number called B. And so if there was just one exponential decay, if we took the log of the signal, then we should get a line. So let's take the log of the signal as we change B. So we don't know what D is. We'll just sort of say we're recording one slice, the same slice, and so whatever the D was, it's going to be the same. And then record it with a whole bunch of different B values. And remember, the B value was this combination of how long the gradient lobe was on, how high the gradient lobe was, and what the spacing between the positive and the negative gradient lobes was. So that all gets combined into B. So let's just put those in here. So it's like delta T, that's how long it's on. G, that's how high it is. And then big T, that's the time between the lobes. So if you do that, you ought to get a line by rights if there's actually just one exponential decay due to, one diffusion coefficient in your slice, whatever your slice is. And so if you record, say 150 different B's, what do you get? And plot it on a log scale. Well, you sort of get some noisy things like that. And you get something like that. Now, eventually, there's a noise floor, because as you go to really high B's, like B equals 10,000, which we can do, you can barely see the image, because as you turn up all these things, what do? They dephase the signal. And so the more diffusion weighting you have, the lower your signal is, because you've just messed up the phases even more. And And so as you turn up your B signal, your image will get worse and worse and worse until you can barely see the brain in your image anymore. And so there's a noise floor, so we'll call this, the noise floor. But before we get to the noise floor, what you can see, if you actually look at this data, this is more or less what the data might look like. What you can definitely see is that there's a bend. It starts off kind of straight, and then it bends before it hits the noise floor. So there's like a bend, which means if you see a bend, it means, not single exponential. Now, if you just look at a fall off like that, it's hard to tell whether or not it's exponential or not. So that's why you would plot it you would take the log of it and plot it and plot a line through it to see if it actually is a line. So it'll still have this general shape, even though there'll be a bend when you take the log of it and plot it. So it's good to just go into MATLAB and just sort of mess around with it. And one way that you could model something like that had more than one exponential in it is basically just add two exponentials to each other. So you could model the signal is basically the signal, equals the amplitude of one exponential minus B over diffusion coefficient 1. And then in the same voxel, we've got the amplitude of a second exponential minus B of diffusion coefficient 2. So those are simple equations. You can just plug those into MATLAB and just see what these curves actually look like. And if you plot one curve like that one would be like a low D. So we're starting here, and here's one. A low D, sorry. So this would be a low D. Like intracellular, and this one would be a high D, falls off quicker. That would be like high D, like extracellular. So if you plot, two different Ds, and then just add them to each other with some kind of weighting factor for how much of each one you've got, because you've got another variable in there. What do you get? Well, you get something that looks like an exponential in between. So that's what I'm saying is if you just do that in MATLAB and look at that, you say, it looks a sort of exponential-like, but it's not, because if you take this, so this is just the signal, and just take the log of it. So here's the signal, just generate the signal, a real exponential. And then, just plot that same thing on a log scale. What do you get? Well, you'll get something that looks like one line, that will be the one that falls off fast, and another line, and then you'll see something that sort of curves. And that will be, this will be this will describe the curved one, and this one is, log of signal. So we know from the actual data, this is actual data, that there's more than one kind of a diffusion happening within a voxel. You can obviously see the problem is now we've just multiplied the loaves and fishes, and now you've got like a bunch of extra variables. Now you have to fit 2 Ds within each voxel, and then there's the proportion of each of those, because there might be different proportions of extracellular and intracellular in different voxels depending on how many cells are there. And so now we got 4 numbers to fit instead of just 1 D. So you can quickly see that you need to make a lot of measurements. So what do people do? They typically will measure 3 Ds. 3 Bs. So here's B number 3, here's B number 2, and B number 1. So you might measure like B equals 500, B equals 1200, B equals 3000. And so you have 3 different B measurements. And then from that, you can, obviously 2 is not enough. You just do 2. You can always sort of fit a line through that. So you need, if you want to see whether this line is bent, you need at least 3, roughly, to do this. But you can see quickly this is going to make your life miserable, because if you're going to measure 60 directions, and then you're going to measure a bunch of B's at each direction, obviously that can get sort of hairy. But that's a general sort of introduction to this idea of looking, and there's many different acronyms for different ways of doing this, but basically this is what underlies it, is you've got multiple different diffusion coefficients going on in the same voxel, because there's different kinds of stuff in there. And so, and we know from like careful measurements like this that you can't really properly characterize what's going on there using a single diffusion coefficient. And so you really need to, if you really want to more accurately characterize what's going on there, you have to take more measurements. And what kind of more measurements are they? It's not directions here. It's, well, you still have to collect a bunch of directions, but it's changing the B value. And so that's the reason for multi-B type experiments, where you're trying to sort of characterize the length scale of what kinds of multiple things are going on in each voxel. Okay, so any questions about sort of multi-B? Why do you want to collect multi-B values? So, you generally what you're talking about is, if you're in a dendrite like this, and here's an axon versus, so if you have like a molecule outside in the fluid surrounding the cell, there's not as many proteins in that, and so those guys can kind of like wiggle around more. Whereas a molecule that's inside the cell, especially one that's inside the axon, it's constantly bumping into the walls. So it can diffuse. Maybe it's diffusing more in this direction, but it's constantly ramming into the walls, and so that's going to slow down the whole, the general. It's going to change the D. So you have a different D for those situations. Okay, so length scale. Good on the multi-B. So a lot of protocols are set up to record, multiple diffusion images, not only with different directions, but also with different B values. If you're just trying to do tract tracing, probably, one B value is better, and one that's not too large of a B value, so it doesn't make your images too noisy. Okay, so now, what do we actually do when we record diffusion sequences? So first, I'll put up a standard one, and then I'll put up like an advanced one. So the first diffusion sequence that I drew was one with just a gradient echo, but that turns out not to be a very so remember that one was, do an RF pulse, and then you turn on a diffusion lobe, then you wait for a while, turn on the opposite diffusion lobe, and then collect the image. And the idea is that this one will fix whatever that one did, as long as everybody stays in the same place. If you diffuse, the signal goes down, attenuation. So one of the problems is we need a lot of time for the diffusion to occur, and gradient echo falls off pretty quickly. And so if you could work spin echo into there, then that would help you. And this, I can't remember the something Tanner. I think that's how it's spelled. I can't remember. That's the name of that. Something like that is the name of this sequence. And so this, for this one, we just do a spin echo. But that complicates things a little bit, because remember, the spin echo goes to the conjugate point in K-space when you do that 180. So first we do our RF. So here's, RF in and the three gradients. RF in and the C, Y, X, RF out. So the trick here is, first we, select a slice. And then, start off with a 90, so we get the biggest signal possible. And then we do our diffusion encoding. And the diffusion encoding, remember, we only got to do a hemisphere, so we can put all the gradients upward. So here's a giant diffusion encoding gradient like that. But remember, we got to test a bunch of different directions, and so we'll have to use different levels of that to indicate different directions, and we'll also need them on all the gradients, because remember, we have to measure a whole hemisphere. So that means we're going to have to sort of do all a bunch of different combinations of x, y, and z gradient. Then what we do, so that messes up the spins, and now we're allowing the spins to diffuse with the hopes that we'll get some attenuation. And then what we do is we do a 180 here. So when you do the 180, in order to make a spin echo, so that means that at this, let me just spread that 180 out just a tiny bit more. I have just enough room. So now we do our 180 right here. And so that means that amount of time, tau after, this is where we'll expect to get our spin echo, down here. But now we've got to fix the result of wrapping up the spins here with the hope that some spins will diffuse and they won't get fixed up and they'll be attenuated. But we've done a 180 in between, and so it turns out we have to do the same sign again. So normally, the original, more clear to understand pulse sequence was we do a positive gradient, wait for diffusion, then do a negative gradient to fix it. So the way we fix with a 180 in between, the way we fix it is by doing the same sign gradient, because the 180 kind of flipped us to the opposite side of k-space. And then we have to put the little funny ears in order to select this slice. That selects the slice. So what comes out is we get like a really big FID, which immediately gets squashed by the gradients, which we don't record. This guy hopefully shouldn't give us anything if it was a good 180. And then here's where we're going to get the echo. But now we're going to typically want to record a lot of different directions, and so we'll use EPI to do it. And so the EPI will be, it's going to be those up and down trapezoids. I'm going to have to draw, there's going to be 64 of them, so they're going up and down very rapidly like that. And then here's the little blips to sort of allow us to record all the data for one slice. And so then this time, there'll be like a zillion little echoes for each time you go across k-space. So there's a bunch of echoes, here, up and then when you get to the center of k-space, it's the biggest echo. And so this is our TE effective. So this is one slice, and then we're ready to let that one recover because we did a 90, and then do another slice. And so that's how our standard DTI pulse sequences on the scanner are basically look like this. So you mess up the spins, wait for diffusion. In between, while you're waiting for diffusion, do a 180, then unmess up the spins, and now you're prepared. So that's this is the preparation part. This is, prepare on this side, prep going that way, and then, read out image on this side. And you can do multi-band type thing where we select 3 slices at the same time, or 4 slices at the same time, and then do that slice grappa, all that business in order to sort of go even faster. And it's always good to go faster because, we've got 64 directions, so we have to essentially acquire the whole volume of the brain, but 64 different times, kind of like a functional MRI scan. So that's a standard, spin echo, spin echo DTI. And so that would take, to do 64 directions, it might take, say, 5 minutes. You typically want to do each direction a couple times. So one of the problems with diffusion is that I mentioned earlier was this idea of eddy currents. And eddy currents are currents that start sloshing around in the metal of the magnet as a result of these very large gradients. And their time constant, can be 50 to 100 milliseconds. So that's a long time. So one of the problems that those things cause is they mess up the B field, they cause a Fourier phase shift, and that causes the image in certain parts of the image to because they're on for like 100 milliseconds, so they're on for all the different spatial frequencies that you recorded here across the slice, it's going to wiggle the slice around. And so as you go to different directions, you'll see like the front of the front of the brain just going wiggling around as you page through the different directions. And so that's a problem. And so people have worked out all different ways of trying to improve pulse sequences to try to cancel out some of the eddy currents. And so I'll just draw out a really complicated one here, but it's kind of cool. So if you want to read, this was there's a guy I worked with back in London et al. 2014. So here's our main gradients again. So this one has stimulated echoes in it and spin echoes. So first we do a 90 degree, and then after not too long we do a 180. So here's 90 and 180, and here's our first tau 1, and that amount of time after that we would expect to get a spin echo. And then we do a different amount of time here. So that's tau 1. So that's a different amount of time, and do another 180. Now normally you would do just 2 tau 1s in there to get the echoes all on top of each other, but in this case we for our eddy current reasons, we want to get a sort of an asymmetrical setup. So there's our second 180. And then what would we expect from those 3 pulses? Well, we would expect that tau 1 after this one, you ought to get a stimulated echo, because remember that's something you get from 3 pulses. So the distance between the first and the second pulse after the third pulse, you get a stimulated echo. So there's going to be a stimulated echo down here, and then we also going to get a secondary echo from this guy. So here's so tau 2 later, you'd expect to get, you can call it a doubly refocused echo. So you get a second spin echo. So why are we spreading it out like that? Well, part of the reason is we want to mess around with the gradients to try to deal with the eddy currents. And so the first thing we do, so here's our RF in G1, GZ, GY, GX, RF out. So the first thing, turn on some diffusion lobe, and we can make these diffusion lobes slightly different length to help us out with some of the eddy current business. And so we have to sort of do the little ears business here to select the slice. So this guy is one of the diffusion lobes. Let's make that one a little bit bigger. And we're going to have to do all different directions. We're doing 64 directions, so we need to do a lot of different directions. And then we need some crushers in there. So Let's start putting some crushers in there to sort of get rid of some of our excess magnetization we don't want. And then we did a 180, and so now we do a longer one like this. Okay, so what's going on here? So now we're actually messing up the spins further. So the idea is this messes up the spins. We did a 180, and since there's a 180 in there, doing a positive one is equivalent to doing a negative one before the 180. So this further messes up the spins. And then we start unmessing up the spins. So this guy is the same size as this one. And then after this one, we've got to reselect the slice again, like that. And then do one final one to fix up this. And this one is positive because there's two 180s in between it. So that's the complicated pulse sequence you get. And then we have to do, since we're doing all these different directions, we've got to do the same thing on the other gradients too. So here's all the different diffusion directions that we're using for different. And then there's a bunch of these crushers, and those crushers are all arranged so that they're perpendicular to the diffusion direction, other messy things. Put those in there. So you can begin to see, like, there's lots of fiddling. So we haven't done any echo recording yet, and so if we look down here, we would have gotten a huge FID, which we're ignoring, and then at this point we would have gotten a spin echo. We're also ignoring that one, and we're using this one as if it was an FID. And so then what will happen is if at this point, at this point here, T2 after that, so pretend this one was an actual FID because everything comes into phase. What will happen is that amount of time after the 180 over here, we'll get a secondary echo. So this is our secondary echo. And then T1, tau 1 after the third pulse, we'll get a stimulated echo. So this is a secondary echo, twice refocused echo. Twice refocused spin echo, that's what it says in the paper. This guy's a stimulated echo. And while those are going on, then we do our EPI readout. So this whole thing up until this point was just the preparation. So this was, prepare. And then here's image. And those echoes, they aren't centered, but that's okay, because remember the Fourier frequency shift theorem. If we've got frequency shift of the echo, not a problem, it just sort of messes with the phase. So now we have to do our EPI like readout. And so starting here, we will go to the left side of K-space and then go rapidly back and forth K-space, 64 times back and forth to record all our data. And then here's the little blips in the phasing code direction. And then I forgot, we have the, before we do this, we should do some navigators. Because remember, got to have navigators to sort of figure out, to deal with the sort of drift in the B0 field. And so this guy is EPI. So that's an example of an actual, and there's some more echoes that we're throwing out because, remember there's like, spin echo, there'll be, spin echo 2, 3, spin echo 2, 3, and there'll be another one, out here that we'll also throw out, spin echo 1, 3. so this one, so our effective TE time will be to the center of k-space, so wherever that is. So I think we put the secondary echo in the center of k-space. Okay, so here's our blips, like that. So this is our effective TE. So this guy was spin echo 1, 2, which we threw out. And so this is our TE effective. So why would you go through the trouble of doing this? So you've got gradients going in different directions, different lengths of gradients, and this is a way to sort of cancel out some of those eddy current problems to get more stable images that don't wiggle around. Because it turns out it's quite hard to fix distortions in DTI images, because the problem is each different direction has a different contrast, and so you can't easily align one direction image to another direction image because they're not the same, because you've done diffusion encoding. And so it turns out to be quite difficult to post hoc correct distortions in diffusion images. And so if you could somehow do something to reduce the amount of distortion beforehand, that would help. I mean, one way of trying to correct the distortions is go through Y k-space in the opposite direction, and that will flip the distortion. So you'll end up with one image where it's bent to the left and another image where it's bent to the right. And then using those two images, you could try to sort of put them together, but of course that means you have to collect more images. So if there's any way to sort of get rid of the distortions before you've introduced them, that's always preferable. And so this is an example of, the additional nightmare that happens when you try to optimize things. Okay, so any questions about practical? So we did, tract tracing, length scale, multi-B, and then sort of practical diffusion pulse sequences. Oh, good. Okay.